Mr. Townsend, do we need to staple 8 and page 1 together?
Just make sure your name's on both, or staple it. It doesn't matter to me. I just need to make sure I can get them back to you. But I have no preference.
Same height as me.
Are we turning in 10 too? Like 8, 9
Not today. Okay, I am looking for 2 of your assignments to be turned in, so if y'all have not done that before the bell here, make sure that you have it ready to give to me by the end of the minute of silence.
You're going to the library.
Morning. Glad to see you guys back. I think I said this last week, but in case it was a different class.
Good morning, FHS. This is Dr. Miller. I hope everyone enjoyed the long weekend and got some well-deserved rest. I want to start by saying, great job on the first 2 weeks of this school year. You've set a strong tone for what's going to be an amazing year. Just a quick reminder as we get back into the swing of things, please continue to wear your ID every day, and remember there are no cell phones allowed in class during instructional time. We've got some exciting events coming up. Our first Cup Rally is this Friday for 9th and 10th graders during advisory. We also have a home volleyball game tonight. Be sure to show up and support our volley dogs. Let's keep up the positive energy and focus. Together, we're going to make this our best year yet. Go Purple Dogs.
Okay, what I was saying is, I think I said this to y'all last week, but sometimes the intercom speakers don't work. I don't know. Like, you could hear the pledge didn't work, the minute of silence didn't work, but then her announcement did. So sometimes it's going to be super light in the mornings, but I don't really know why that is. Okay, last call. Any other assignment 8s and 9s? Anybody that came in near the bell? Last chance before it is late credit. If you turned it in the Google Classroom, that's fine. You don't have to do both. If you do Google Classroom, I don't have to have your hard copy also. Okay, then we are starting to round out the end of this unit. So we do not have our quiz next class, but it will be the class after. So one of the handouts you guys picked up today is the unit review number 13. I don't know if I numbered that one for you. Yes, I did. That one's a little bit longer. So we'll have to talk about how far you need to be on that by Thursday. You won't have to be 100% complete. But of course, if you are, that will just make class on Thursday a little bit easier. I want to give you some time to finish up the continuity that we talked about last class, and I'll do a quick little reminder on that. I want you to practice finding the different types of discontinuities, which I just barely 45 seconds mentioned those to you last class. So before we do that, we will do this last of the new handouts, assignment 12. But just in case, you can see I didn't ask you to turn in assignment 10 yet, and that's just me trying to be as fair as possible to you. I know you were finishing that up at the end of class last time I saw you guys, and so there's a good chance you had some questions on a couple of them, and you didn't know about those questions until you left. So, is there anything that I can help you finish up on assignment 10? When you went to finish it, check your answers. Was there any of it that you struggled with or would want a reminder on before we start getting close to the test? Okay, now normally I would move on because hopefully you guys are circling or starring or something the questions you need help with, but I'll give you a little bit more time to just double check since it's still the start of the school year. Okay, then let's talk about a quick little review over assignment 11. Assignment 11 was where we started talking about what it means to be continuous. How do you prove something's continuous, or how do you prove something's discontinuous? So there was this 3-part definition. Again, we did this last class, but we didn't practice any of it. I just had you take down the notes. So we talked about there was a formal definition. You absolutely must memorize this definition. Trying to justify why something is continuous at a point or not discontinuous at a point without the definition is just a waste of your time because you're not going to do it comprehensively. So basically the point has to exist. If there's not a point, there's a hole. The limit has to exist because if the limit doesn't exist, it's not approaching the same number from the left and the right, which means your graph is jumping around. And then just because you have a point and just because you have a limit, if that point's not the same as the limit, then there's still that break in the graph. So we thought about at -1, we plugged in -1 to both of these to see what their y values were. If it was 4 from the left and 1 from the right, then we could see that it was jumping, so it's definitely not continuous. But this is the justification. Don't say because the graph is jumping. That's not a mathematical explanation. And then in part B, we checked that x equals 2. So I plugged 2 in here, saw that both were 4. It had a point there, and the point was equal to the limit. So notice I stated all three things were true, which is why I can say for sure, yes, it is continuous at that time. Okay, we talked about types of discontinuities, but we're going to dive deeper on that on today's handout anyway. So basically there is 3 types you need to be aware of. If your whole graph jumps, like this one, it's called a jump discontinuity. If you have a vertical asymptote, so your graph goes to infinity and negative infinity, we refer to that as an infinite discontinuity. And then the one that I'm worried about you remembering, this will be on your quiz next week too. Probably just one question, but I'm more worried about you remember it in 5 months. If there's a hole, so this is kind of what this one looked like. The limit existed. It approached -2 from the left and from the right. But x equals -1 had a y value of 5. So my whole graph's not jumping, it's just jumping at a point. But if you have a hole, it's not called hole discontinuity, they call it removable discontinuity. So that name is not intuitive. That one you certainly should mark up in your notes to make sure you glance at that before the quiz. Okay, so in just a moment, I will ask you to go and try those and make sure all of that's working out for you. Okay, but here's basically the last new piece before you can be in full review mode for this unit. Okay, and so this one just focuses on the types of discontinuities. So even though I briefly talked about them and you briefly put them down in your notes, we need to practice it a little bit more and actually go about finding them. So to be continuous just means you have a nice smooth graph. Any point you know on that graph, there's going to be a point before and a point after it. No sudden jumps, no sudden holes, no sudden vertical asymptotes. Whereas something that is discontinuous is going to have one of those type of breaks in the graph. So if you have the graph in front of you, usually you can just eyeball it and see pretty quick whether it's yes or no. But so to recap the notes we took last class, let's do these two first. Number 2, if it's going to infinity and negative infinity, then at that point we would say it has an infinite discontinuity. If, question 3, your whole graph jumps, that is called a jump discontinuity. And if there's a hole, whether there's a point somewhere else or not somewhere else, doesn't matter. It's not called hole discontinuity. It's only referred to as removable discontinuity. Now, technically, I have seen some questions like this where we need to update this a little bit too. This is the only removable one, which implies that these two are known as non-removable. So the holes are the removable type. The other two are sometimes referred to as non-removable. That's important that you're aware of that, depending on the question. Okay, so we need to review just a touch of rational functions here so that we can tell whether we've got a hole versus a vertical asymptote, so we can describe what type of discontinuity is occurring. So if we don't have the graph and instead we have a function, I've got to think about what numbers make the numerator 0 and what numbers make the denominator 0. So the quickest way to do that is to factor both. Think about what numbers make the denominator 0, and think about what numbers make the numerator 0. Now, those of you that did pre-cal last year, we reviewed this. This was actually our very last topic of last year, so it should be a little more familiar to you. But they still ask you about this on the AP exam, about holes and vertical asymptotes, even though that's not really a calculus topic, so I don't know why. But anytime you had 0 divided by 0, that's how you got a hole. So if there's an x value that makes the top and the bottom 0, at that x value there's a hole. But again, we don't call it hole discontinuity. We call it removable. Make sure you're practicing that so that it sticks. The one that doesn't matter as much is if it just the numerator went to 0, then your whole fraction was 0. And when your whole fraction is 0, y is 0. And when y is 0, that's when you get x-intercepts. We don't really need to know that for today. But then if you had a number that made the the denominator 0, but not the numerator 0, this is how you get the vertical spikes in your graph, the vertical asymptotes. Because right before you divide by 0 and right after you divide by 0, your fractions go into infinity or negative infinity. So if there's any numbers that make just a denominator 0, it's a vertical asymptote. And so if you're asked what type of discontinuity is there, you would say, well, x equals -5. It is an infinite discontinuity. So there's your two answers. But again, you have to remember how to find a hole versus find a vertical asymptote. Holes occur for x values that make the numerator and the denominator 0. Vertical asymptotes are x values that make just the denominator 0. If you don't have that ingrained in your brain, you need to jot that out to the side. Also, this is a big ACT topic too. So if you are trying to raise your ACT score, you really need to know that for the ACT anyway. Okay, so now...
Hold on, can you... Thank you. Alright, that's good.
Okay, so now I'm going to say the exact same things, but just a touch faster because now we've reviewed that. You need to think about what numbers make the numerator 0, what numbers make the denominator 0. That's often going to include some factoring. Difference of two squares, difference of two squares. But looks like there's one number that makes the numerator 0, two numbers that make the denominator 0. So if there's any number that makes both the numerator and the denominator 0, visually that's going to create a hole in the graph. But for our calculus answer, we will say when x is this, we have removable discontinuity. And then if there's any number that makes just a denominator 0, that's how you get a vertical asymptote, which is where your graph's going to infinity and negative infinity. So the calculus behind that is we would say at that x value, you have an infinite discontinuity. So a little different way to state your answer.
So if you have a hole, then most likely the remaining number on the bottom is going to be your answer for vertical asymptote.
If you have a number that makes the numerator and denominator 0, that's how you get a hole. If you have numbers that make just the denominator 0, that's how you get vertical asymptotes.
So vertical asymptote is done after the hole. You find the hole, though.
Yeah, it's safer to do it after the hole, yes. You don't want to think that there's two vertical asymptotes here. -1 wouldn't be a vertical asymptote. And of course, you can graph these in your calculator if y'all want to see a visual of them. But again, basically it amounts to, well, actually number 3 is pretty tough. Let's come back and do 3 last. Basically it amounts to, you need to think of this as one big fraction. Think about the numbers that make the numerator 0, what numbers make the denominator 0. So if I write this question 4 as a fraction, when does the denominator equal 0? So does it have any holes? So then it doesn't have removable discontinuity. Does it have any vertical asymptotes? Then it doesn't have infinite discontinuity. So basically, what numbers can I not plug in for x here? You can plug in anything you want to, right? You can plug in anything squared and minus 1. In fact, that function is so basic, you guys should know what that looks like. It looks like x squared shifted down 1. This thing is always continuous. You're only going to get breaks in the graph when you try to divide by 0. Now, what type of break, what type of discontinuity depends, but discontinuities occur when there's a break in the graph. Okay, let's go back to question 3. So one more example here, and then I can let you go back and work on that continuity thing. Okay, so this one is just a little bit harder to solve. Those of you that didn't do pre-cal last year are definitely going to struggle with this one, because I think even those of you that did will struggle to remember all of this, but that's okay. It's good practice for us. So that I can work it like I did the other 3 questions here, I'm going to rewrite tangent as sine over cosine. Now, to be fair, of all of the trig stuff you had to memorize in pre-cal, most of that stuff they don't expect you to memorize for calculus. Knowing tangent to sine over cosine is one of those. If you don't have that memorized, you better put it at the top of your page and know it as soon as possible. So basically, I'm going to think of this like I did the other questions. I'm going to think about what numbers make the numerator 0 and what numbers make the denominator 0. So let me do the numerator first. When does the sine of 2x equal 0? Now, in pre-calculus, how I suggest students to do this was to pretend like it didn't say 2x, pretend like it just says 1x, and then from 0 to 2 pi, you could go around the unit circle. You could name everywhere where sine is 0. That's where the y value is 0. And then you're going to be tempted to say that's at 0. Oops, I'm just going to do it one statement. 0, and then if you add pi, you get this one, and then if you add pi, you get this one, and if you add pi again, you start getting coterminal angles. But the problem is, I only pretended like it was x. It's actually 2x. So we have to go back here and say, wait, I know what 2x equals. So the numbers that make the numerator 0 are integer multiples of pi over 2. So when n is 0, we get 0. When n is 1, we get pi over 2. When n is 2, we get pi. When n is 3, we get 3 pi over 2. And when n is 4, we get 2 pi. Also, this is kind of weird. Obviously, I didn't make up this question, but typically you either include 0 or include 2 pi, since those are coterminal. You don't usually include both. But. Okay, now I need to do the same thing with the denominator. I need to see what numbers make the denominator 0. So once again, I'm going to temporarily pretend like it's an x instead of a 2x. At least mentally, I have to go around the unit circle and mark everywhere cosine is 0. That's pi over 2 here, plus pi, plus pi, plus pi, plus pi. So plus integer multiples of pi. But before I use that, I need to slow down and say, wait, I solved for 2x, not x. Now divide everything by 2. And here's a formula that tells me all the numbers that make cosine of 2x equal to 0. It could be pi over 4. And then I could add pi over 2 to that, which would be right here at 3 pi over 4. I could add pi over 2, which would be 5 pi over 4. Add pi over 2, which would be 7 pi over 4. And then add pi over 2, which is bigger than 2 pi. So, as I said, that's, I don't know, that's definitely one of the harder things even in pre-calculus, because you better know the unit circle at that point, and you have to practice doing that. So all of that to figure out which numbers make the numerator 0, which numbers make the denominator 0. So it looks like there's no numbers that make the numerator and the denominator 0. So there's no removable discontinuity. But at x equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 give me division by 0. Which would be infinite discontinuity. So you can see that the difficulty of each question can change quite a bit, but the parts that were consistent, you have to solve for the numerator to equal 0, denominator to equal 0. Remember what happens if it's 0 over 0 versus some other number over 0. And then the last piece is the calculus. If it's this type, call it removable discontinuity at those x values. And if it's this type, call it infinite discontinuity at those x values. So again, how hard that is just depends on how good you are at factoring, solving quadratics, knowing your parent functions, your unit circle, your trig identity. I don't know. The better you are at that stuff, the easier these should be. But okay, so now I need to have you guys practice some of this. So first up, I would like you to go back and try the questions from assignment 11. That was the definition of continuity. Again, we took those notes last class, and I reviewed them for a few minutes ago. I need you to practice those question types first. That way, as you find questions, other people are looking at similar questions. As you finish that one, you can work through assignment 12, the types of discontinuities that we just looked at. And then as you finish that, go ahead and start 13. But I will obviously tell you exactly where you need to be by Thursday at the end of class. For now, just go ahead and get started, and I'll get these homeworks put in, and then I'll offer to help. figure out if it's continuous at -1.
Yes.
Okay, so what value is it to the left of -1?
Up to -1 is
Okay. Which is,
1 x plus 1 divided by x squared.
okay, but at -1 it's,
-1 -1/3. So it's not.
okay, so here it's 1/3, and then from the right it's,
1/3.
okay, well 1/3 is 1/3.
It's like on the second step down. I'm just talking about this step.
Does the limit equal the point?
Yeah.
So what is the y value when x is -1? Not limit, but the point.
Oh, that's fine.
Plug that x value into the function.
So it's like 3 -1.
Which one are you plugging it into? You shouldn't be plugging it into this one, because this is not when x equals -1.
Okay. So it'd be 1/3 or -1.
You're plugging the x value into it.
So it'd be this thing. So
Okay.
it'd be,
So think about the definition. Does the point exist?
yes,
Does the limit exist? Does the limit equal the point?
yes,
Did you say all three of those things?
yes.
Okay, then your answer is yes, and then showing those three things is your justification. So that is what you need.
Yeah.
Yeah, as you guys are working on that one, make sure you're not just kind of guessing yes or no whether you think it's continuous. You should be thinking about the definition. If there's not a point there, say it's not continuous because there's not a point there. If the limit from the left doesn't equal the limit from the right, say it's not continuous there because the limit from the left doesn't equal the limit from the right. The third part of the definition, the limit has to equal the point. If the limit doesn't equal the point, say that and say it's not continuous. Otherwise, you should say it is continuous because there is a point there, the limit does exist there, and the limit does equal the point there. Any other mental gymnastics you're trying to do is probably down the wrong path. You need to be specifically using the definition.
Number 7, it jumps from 1/4 to 3/4 after it was -2. So I say it's a jump this coming, we're going to stay, well, I wouldn't say at -2. Is it the jump this coming? Oh, what? No.
So the limit from the left is before it, and the limit from the right is,
It's
okay, so you've already figured out it's going from here to here, it's jumping. So I say it's not continuous, and my explanation is the limit from the left doesn't equal the limit to the right. So
Well,
say
that's-
let's ask them this way.
Yeah, it was just asking, to identify the type of discount where on the back.
Oh,
I just didn't know if I'd say just add -2 since I -2.
yeah, because it's probably continuous other places. It's at that -2 that there's no problem. So yeah, you should say that.
ln1 equals 0?
It does. Yeah, you need to memorize that one. limit, you can see it's approaching 0 from the left and the right. And the point is way up top. The line doesn't equal the point. Now here, it's a totally different angle. It's the left and the right is not the same. Oh, you're looking at the left. Four. I'm trying to do 1 to the 4, which is 1. 17 minus 16, which is 1. So we eliminate this. There's a point at x equals 4. 1 to the 4. And point is 1. And limit 1. Divided by this continuous. Let's match them with all those up. Sign sheet. Okay, so what's the limit? Okay, so there's certainly a jump there, but also 3 is somewhere in the middle, so it's definitely not continuous. I would say it's a whole. Oh, I would call it a jump. At x equals -2, since this one's kind of off by itself, but it's going from these values to these values, so I'm going to go with jump right now. Yes, it can only be one type. Yeah. Yeah, so if the whole graph is jumping, this referred to as a jump. Okay, before I pass back to some of your homework papers, let me offer to help out with a couple. So again, right now I'm only looking at assignment 11. So those of you that worked ahead and have more than that done, that's great. But I don't want to take questions on the other ones yet because most people aren't there. Okay, so from this continuity worksheet, which ones would you want some help on?
4.
This number 4? Okay, first part or the second part?
First part.
Okay.
And second part.
Okay, well I'll do the first part for you and then you can try the second part. They look like they're the same type. Okay, so to figure out if it's continuous, again, you've got to do yourself a favor. There is only one good approach to this question type, and that is to think of the definition and try to use the definition. I want to think about, is there a point if I plugged in pi over 2? And since this says when x equals pi over 2, that means I would plug it in here and get cosine of pi over 2. Oops. Which I don't really care what that number is right now, but I care that the point exists. When x is pi over 2, there is a point there. That's one part of the definition. Another part of the definition is you need to think about what it approaches before and after pi over 2. So you need to think about the limit as x approaches pi over 2 from the left, and the limit as x approaches pi over 2 from the right. So again, slow down and make sure you're plugging these into the correct thing. If you're plugging them into the wrong piece of the piecewise function, then you're only going to get it right if you get lucky. So to the left would be x values less than that, so that would be 0. And to the right would be x values slightly bigger than pi over 2, which would be this one. And the tangent at pi over 2 is sine divided by cosine, which is 1 over 0, which is undefined. So it looks like to me it's approaching 0 from the left, and from the right it's approaching infinity or negative infinity. I don't know which one, but I found something wrong with the definition. So I would say, if the question is it continuous there? No. And if I need to do justification, which it does say to do justification in the directions, I just need to state one of these things that was wrong. So the limit from the left of this function was not the same as the limit from the right of that function. And to disprove continuity, or to prove it's not continuous, you only have to state one of the things. You don't need to state all three. Okay, was there something more specific about this one? Landon, this was yours.
No. No.
Okay. Is anybody else going to ask about this one? Need to ask more about it while it's still up? Okay. Again, these questions are going to be way quicker and faster once you've memorized the definition and you instantly try to apply the definition. Make sure there's a point, make sure the limit from the left and the right are the same, and make sure that the limit equals the point. If all three things are true, say yes and state those three things. If any of them are not true, say no and state which thing was messed up. That's the approach you need to take with every one of those type. Okay, somebody else have another question or two?
Do 5.
Question 5. All right, for each function, identify the type of discontinuities and where they are located. So again, this one has 4 pieces. So one thing you need to keep in mind is each one of these pieces is continuous within its domain by themselves. This is continuous, this is continuous, this is continuous, and this is continuous. But they might not be continuous when it hands off at x equals -2, and they might not be continuous at x equals 4 when they hand off from this one to this one. The handoff from one function to the next can mess up continuity. So, I don't know, I would just start thinking of the definition here. When x is -2, y is 3, so there is a point. If there was not a point, that would mean there's a hole, and I could say it's removable discontinuity there. I could think about the limit from the left and the right of -2. I get -2 from the left and -√6 from the right. So, what's it called when it approaches one value from the left and a different value from the right? What type of discontinuity is that? Good. It is jumping. And then, of course, we should be able to say where. It's jumping at x equals -2. Now, there could still be something else going on at x equals 4 also, so I need to make sure that there's not a second answer here. If I plug in 4 for x, I get this. So there's a point at x equals 4. The limit from the left is this. The limit from the right would be natural log of 4. So the limit as x approaches, I need to put that in. The limit as x approaches 4 from the left would be 6 equals 2, which is 18. Those two definitely are not the same. So it looks like it's jumping at 4 also, and at x equals 4. It's jumping at both those places. Now, your calculator does not do a great job of graphing these, but I actually did learn this summer. One of the few things I had to do, well, you guys don't care about all that, but every 5 years you have to do some training, and so I did that, and I learned that your calculators can graph piecewise functions now if you update your calculator. So they just put out a new update, and so you can actually go to y equals and you can actually type this in and make it look like this when you have a calculator. I'm only pointing it out to you because that would be a great way to check this answer, because if you had the graph in front of you, you could visually see those jumps. Okay, is anybody else going to ask about 5 while it's still up? Okay, one more. Somebody who's not asked one yet. Anything else on the continuity worksheet that you've tried and something's not working out?
12.
Number 12. All right, question 12 has a little bit different directions. They're asking us to find out what value of k would make this continuous. So if I FOIL this stuff together, I get that for the top, and I can't really do anything with the bottom, but I guess I'll rewrite it. What is this? Let's say x. Okay, so k is just some generic number. We just don't know what that number is. Now again, it's unfortunate, but this is a lot of what they do to you on the AP exam. They throw little things in here that make the questions a little bit more uncomfortable. But underlying math should still be the same. So for these to be continuous, what has to be true about these two things? They need to be equal. Very good. So again, I have no idea what this one looks like. I have no idea what this one looks like. But notice at x equals 1, if my red graph looks like this and my purple graph looks like that, you would quickly say it's not continuous. And the problem is this is way down here and it needs to be way up here. So when x equals 1, you need these two to have the same y value. So that's why you would set these two equal to each other. And I really could care less if they're equal the rest of the times. I need them to be equal at x equals 1. So you're going to plug in 1 for x. And now we're left with an equation that only has k stuff. So let's combine all of our like terms. It's a quadratic, so you want everything to be on one side set equal to 0. Factor. And that looks like that happens when when k is -2 and +5.
Wouldn't it be k squared minus 5k?
Where are you getting minus 5k?
Because you're subtracting k from the...
What about these 2k's though?
Okay.
I said this plus this would be -2, and then when you subtract this one over, it would make a -3. Does somebody have the answers in front of them to check? There was 2 answers. Okay.
Yes, k equals 5 and k equals -2.
Now again, I promised you I was going to make you sick of hearing this, but looking at this question, I had to understand why I set those two equal to each other, and then plug in x equals 1. But 95% of what I had to write down and work out is just regular old algebra stuff. Combining like terms, evaluating an x equals 1, solving a quadratic, so you put everything on one side set equal to 0, factoring, solving linear factors. Most of the work is old stuff. It's just, calculus is a lot of trying to figure out how these pieces fit together. Okay, did that address your question? Okay. Okay, it seems like you're running a little bit lower on those, so I'll give you a little bit more time and let me pass back these homework papers so that I don't have them, and then I'll offer to help out some more. Obviously, once you finish up with this one, make sure you've checked your answers before you move on, but then you can move on to the discontinuity sheet that we took notes on this morning.
seeing this one this year? No, that's not yours. You got 2 waters.
This is electrolytes and creatine. And this is water.
Creatine's not good for you.
That's not true.
It
It actually has many health and mental health benefits. Increases cognitive function.
Sounds like you've been watching the commercials.
But I've actually been watching a doctor with a PhD in exercise science.
Okay. Couldn't find the first page with this one.
Okay, you should have your homework back now, unless you turned it in Google Classroom, of course. And based on the questions you guys asked last time, it looks like you're getting kind of close to finishing this one. So what else on the continuity worksheet can I help with? Okay, I'll give you a little bit more time here. And I will ask again before you go.
I updated it, but you still need to do that one.
Okay. Authoring again. Any from this continuity worksheet? 13. Okay. Let me think about this one a second. All of these test prep questions are going to be a little bit harder. Okay, let's go with that. Okay, so we've got F and a table of some of those values, and we're trying to figure out which of these must be true. So not could be, but must be true. So I guess to start with A, to be continuous at -1, there needs to be a point at -1. So when you plug in, 1, plug in 1, you get 3, so there is a point. The second part of the definition says to be continuous at x equals 1, it's got to approach the same number from the left and the right of 1, which is not happening. So one part of the definition messes up there, so it can't be that. Okay, so try B. When x is 2, y is 8, so there is a point there. As x approaches 2 from the left and as x approaches 2 from the right, they both approach 5, so the limit is there. And the last part of the definition, whatever the limit approaches 5 has to equal the point, which is 8. So the last part of the definition messed up for part B, so it can't be that. Okay, and then x equals 3. When x equals 3, y equals 1, so there is a point. It approaches 1 from the left and 1 from the right, same number, so the limit exists. And the limit approaches 1, and the point is at 1, so the limit equals the point. So all three parts of the definition work for part C, so C has to be correct. Is that enough? So once again, if you guys don't memorize that three-part definition, you're going to be making these questions way harder. You're going to be trying to rationalize it in your head. And you're going to be doing a lot more work to probably get the wrong answer versus just memorizing the three-step or three-part definition. Okay, one more of these for now. Okay, I know not everybody has, but some of you guys have moved on to assignment 12, where we were talking about these types of discontinuities. Has anyone moved on to assignment 12 and found one you need help with? Yeah. Number 6. Is this number 6? Okay, what are we trying to do? Identify the type of discontinuity and where it's located. Okay, so the type and where. Okay, so to think of this as what makes the numerator 0 and what makes the denominator 0, you need to think of this as a fraction. So secant is the same thing as 1 over cosine. So the secant of 2x is the same as 1 over the cosine of 2x. Now I can see that nothing makes the numerator 0. There's no x's in there. 1's never 0. And then the denominator could be a bunch of stuff. This is what we saw on the front page in the notes here. To figure out what numbers make the denominator 0, you probably need to think about cosine x and where he equals 0. That first occurs at pi over 2. And all the other answers are separated by pi integer multiples of pi. So I can use this to start listing out all of them from 0 to 2 pi. The first one's at pi over 2. When n is 1, I would add pi to that, which would be 3 pi over 2. Add pi to that, and that's bigger than 2 pi. So it looks like there's two numbers that make the denominator 0. And so to answer their question, where and what types of discontinuities are there? There's no removable because they're not wholes. There was no number that made the numerator and denominator 0. At x equals pi over 2 and 3 pi over 2, it made me divide by 0, which creates vertical asymptotes, which in calculus is referred to as infinite discontinuities at those two values. Okay. Is that enough for that? Okay, anybody else was going to ask about that one? Need to say something while it's still up there? Yes.
Why is it only at those two values?
Well, that's what I was actually checking while you guys were looking at that. So I went to go graph it to give you a visual, and I did make a mistake in here. It looks like there's 1, 2, 3, 4 times 4 vertical asymptotes. You can see I graphed it from 0 to 2 pi. But I only said that it happened at 2 locations, pi over 2 and 3 pi over 2. So what did I forget to take into account? Right, so I was really trying to solve cosine of 2x equals 0, and I changed it to 1x out of convenience. So what I should have done is said, this is what 2x equals. So now I divide everything by 2. This is the formula I should have been using to find x values. That 2 makes them occur twice as often, so that it's probably there's going to be 4 answers, not 2. So the first one's at pi, and then add pi over 2 to that, so that would be 3 pi over 4. Then add pi over 2 to that. Wait, what am I doing? I'm sorry. Pi, add pi over 2 would be 3 pi over 2.
Shouldn't it be a pi over 4?
Yeah, thank you. Divide by 2, divide by 2, divide by 2. I didn't divide this one by 2 for some reason. So pi over 4 should be the first one. Right here. Add pi over 2, 3 pi over 4, add pi over 2, 5 pi over 4, add pi over 2, 7 pi over 4. If I keep going past that, I'm going to be past 2 pi. So to go back to the graph, which is what I was going to show you guys to try to give you a visual of what we found and how I figured out that I forgot to do something here. So again, here's the graph, and notice at pi over 4, there is no y value. That's this guy. And then at 3 pi over 4, this one also doesn't have a value. It kind of looks like it, but it's trying to say infinity here. And then we said, what was the next one? 5 pi over 4 and 7 pi over 4. So this one should be 5 pi over 4. You can hit trace 5 pi over 4, enter to jump to that spot. And it is another asymptote. It's trying to say negative infinity here. This is, what's that called? Scientific notation. Scientific notation. Okay, and then 7 pi over 4. Trace 7 pi over 4, enter. And notice this one's trying to say infinity, so it's trying to show this asymptote. But anyway, with the graph I could see that there was 4, and so I knew I had messed something up, saying that there was only 2 of them. So obviously that's one of the longer questions because it's got the trig in there. I will also be willing to help you with question 12, but you should really use 6 and the front page as a quick example though. Okay, so these types of discontinuities, is there any others you have ready to ask? Okay, keep going. You still got 15 minutes, so I should still go quite a ways here.
Mr. Townsend,
Yes.
the vertical asymptote and infinite discontinuity are the same thing, right?
A vertical asymptote is a way to describe what it is. The infinite discontinuity is to describe calculus name for the break.
Oh.
So they're 95% the same thing. One is more a calculus way to describe it, where the other is more of a visual way to describe it.
Okay.
Okay. We're getting under 10 minutes here, so I want to make sure I give one more chance. Is there any other questions you have ready to go? Okay. Let me remind you where you need to be on Thursday. So I took questions from assignment 10 today, and I didn't take it up, but I probably will take it up next time. That should be finished from last class anyway, so that's not different. You need to finish up 11 and 12, so it seems like y'all were finishing up, most of you at least, were finishing up continuity about 20 minutes ago-ish. So I need you to finish up this type of discontinuities to make sure you get enough practice with that. And then I need to give you special directions for the review. So you do not have to have all of the review, assignment 13, done when you come to class on Thursday. But you need to do some of it. How much needs to be proportional to how prepared and ready you think you are for this first quiz. If you feel like you could probably take it now and do pretty well, you can probably get by with doing a little bit less of the test review. If you feel like you wouldn't do very well, you might need to do a little bit more. But I need you to do enough of it so when I see you on Thursday, you'll have time to finish and realize what your questions are and get your questions answered, because that will be the last time I see you before that quiz. And if you don't do any of that between now and Thursday, then you won't figure out what questions you need help with, and then you're putting the figuring it out on yourself instead of letting me help you. So do some of 13. It's even fine if you just do some of the easy stuff. Just knock off half of it. It's just the questions you feel most comfortable with. That way on Thursday you've got class time to slow down on the stuff you struggle with, and you have me to help out. So, any questions about the homework? Okay, and then for the class puzzle for the day, was the last one I did, was it socks? That's the last one we did? Okay, I've got two other ones. The first one's kind of optional. It requires 2 people to volunteer that can solve a Rubik's Cube. Is there 2 people in here that can solve a Rubik's Cube that would be up for racing somebody else? Just one? Oh, Hayden, you'll do it? Okay. All right, so if you guys want to come up to the front of the room, we're going to race up here and see who. Come up to the front and go back to back. Up front. So everybody can see who wins. Sorry, I have to rearrange these. My class is on Friday. Okay, and how confident are y'all at solving? How long do you think it's going to take you? 2 minutes? Okay, about 50-50? Both equally confident? All right. What do y'all think? Raise your hand if you think he's going to win. Okay, you got two believers. What about Hayden? 1, 2, 3, 4. Okay, a lot more for Hayden. Okay. Back to back. So y'all can't cheat see each other's work. Ready? Set. And go. Good luck. Now it sounds like he's going pretty fast. Remember, they said 2 minutes, so. Is he gonna get it? You got it? Okay. Who beat you?
I'm not a solid. That's funny.
You good sport. I was just messing with you. Since you had more believers, you got the hard version. Now somebody in my class on Friday did solve this one. I had to mix it up.
I mean, they're intuitive, but I think for
Oh, never solved it. So, obviously I was just messing with him. Trying to wake y'all up a little bit. Okay, we got just a couple minutes here. So, you need to start finding a stopping spot. Today, you do need to go to your normal advisory